Welcome to this lecture 3 of MCS 471 on numerical analysis. So today we will introduce our first problem of continuous mathematics, the root finding problem. We will derive the bisection method and also look into fixed point iterations. So there are two parts in this lecture. We will see how to derive a numerical algorithm, to define it, and then also analyze it. So we will do this keeping in mind efficiency and accuracy, the main two guiding principles of numerical analysis. So in the second part, we will give a geometric interpretation for fixed point iterations, and we will derive a mathematical criterion for iterative methods to converge. So this is the plan for the lecture. At the same time, we will introduce more about Julia functions in the first part, and in the second part also more on the Jupyter notebook. So what is the problem? We want to find a root. So perhaps let's first look at the picture. We have a blue curve, which is the cosine, plotted between 0 and 3, and we want to find the location where that blue curve intersects the horizontal axis. So look at the vertical axis. The cosine is a very nice function between negative and 1. We want to know when this function becomes 0. Now this is a toy problem. We all know that the root is pi over 2. But suppose we don't know this, and we pick 2 points kind of arbitrary, 2 points A and B. When we evaluate at A, so A is a pi over 4, if you look at the legend in red, so the red evaluation gives you a positive function value. B, on the other hand, gives you a negative function value. So we are working with a nice, smooth, and continuous function, and we know that from the intermediate or consequence of the intermediate value theorem that if we have opposite signs of the function evaluations at an interval, then there is a point inside that interval where that function evaluates to 0. So this is a calculus-based numerical analysis course. We use results and methods from calculus very frequently. So this is a theorem that we will apply here in the derivation of the bisection method. So the interval AB is in some sense then also a bound, an upper bound on the accuracy of the root. If you start with a narrow interval, then you know that you have already a good bound on your root. All right, what's the method then? The method is divide and conquer. So we know that if we split the interval in half, that we can find the root either at the right or at the left of the midpoint. So here now I'm also on my example here, I'm working with only one root. So let's assume that there is one root in the interval AB. like in this nice example here. So we see that the midpoint actually also evaluates, gives a positive value. So we can actually discard the left of the interval at the left of the midpoint where also A is positive. We do not look there, but we look at the right point. So we will continue to work with the interval MB. So you can see this as a recursive algorithm. So this is a divide and conquer principle, is a very powerful program solving method. Let's say then the rule. The rule here expressed in pseudocode is that in each step we compute the midpoint and then we redefine the bound of the interval that includes the root. So the subtitle for this method was bracketing a root. So you can also see this interval as kind of a bracket that encloses the root. So we have a rule. So we had an idea for an algorithm based on a theorem in calculus. We have now a rule. We still don't have an algorithm yet. So it's an iterative method, and iterative methods, they can go on forever. So we will have some stop criteria. So the stop criterion, the obvious one, is that we don't want to do a work that is unbounded. So we have an upper bound on the number of bisections. So that's kind of regulating the cost. But then we have two other criteria. We have a criteria on the function value, and this could be the natural stopping criteria. But we also have a bound on the size of the interval. Why do we have two such bounds? Well, we can have functions that are like this. So this is a function that is very, very steep. And we can have functions that are extremely flat. So I'm exaggerating here a little bit. So here we have a function that is flat. So with very flat functions, we can still allow very wide intervals. But if this is all very close to zero, then we shouldn't bisect much further. So in the case of very flat functions, we can very well deal with the function value. But in the case of very steep functions, we actually need to, we may look at the size of the interval. So the design of good stopping criteria is very important in the design of good numerical algorithms. All right, so we are ready to write down the prototype of our function. Julia is kind of very nice in the sense that the documentation strings come prior for the function prototype. So this actually means that you start writing the documentation before it gets too technical. So here I expressed in words what the function does and what the stopping criteria are. And what it is assumed, so it is actually the precondition. So we are having a continuous function that takes opposite signs on the interval AB. A bit of an oversimplification, we had an epsilon and a delta. I'm here using the same value for epsilon. Numerical algorithms can fail, so they may converge too slowly or they may diverge. So it's important to keep that in mind when you design a function. So that doesn't mean that the function itself is wrong. A difficulty with numerical analysis that we may have a completely logically correct program, but the output is wrong. So the other issue, coming back to last lecture, all the numbers are actually formatted in scientific format. So for that, we actually use the built-in printf. So this is a very plain educational function, if you like. Functions can take functions on input. Another feature of Julia is that one can help the compiler and specify the types of the functions. Just as Python, one can use Julia as a dynamically typed language where the types are determined during the execution, but it's often much better and you get often much more efficient and also robuster programs if you specify the types of all the input arguments. So we are going to print out the bounds of the enclosing interval and also the indications on the accuracy. So the absolute value of the function and the length of the interval. Then we have the rule that is encoded here with this if-else statement. And this is embedded into a for loop. So coming back to the scientific notation, the bisection method is a very rudimentary method. And even though we work with 16 decimal places, we will not see that high in accuracy. So here I will print everything up to 3 decimal places after the point. The errors are actually printed in a floating point in exponential notation. And we are mainly interested there in the magnitude. So that's why we print them in scientific notation. So the formatting strings should be familiar from Python. Also, if you implemented anything in C. And then there is the string interpolations used in Julia. So this is our first function. It almost fits on one slide. Not at all. In a numerical algorithm, we have to worry about the stopping criteria. And we have to take into account that algorithms may fail. And we not only report success or failure, we actually also, when it succeeds, we actually indicate the number of steps. So we have one full program that is spread out over these 3 slides. So the program is also posted. And here we see one session with the program. So you can see that we get an approximation for pi over 2. At the end, you see that we have the pi over 2 with 4 decimal places accuracy, and that is reflected both in the function value and also in the length of the interval. So the cosine is a very nice function. And we have the steady convergence here. So we will say more about the speed of convergence later, but you can observe, and at this point in time, one is not yet well enough trained to observe this, but you can see that it takes about 3 steps to gain 1 decimal place. So we will declare this as a linearly converging method. And most important, it succeeded. All right, so I made some plots. So we will be using the Jupyter Notebook environment to make plots. We can actually also write pictures to file, so one can also actually stay within the scripting environment. But we are using the notebook environment to document our calculations. So in the first notebook that is posted, I just gave the plotting instructions. So here you see an example. So an example of multiple cells here. So a notebook consists of code. So we have the in here, we have the instructions, we have the output cells where the plot is, and then we have text cells where we can put headers and where we can tell a story. So these are the markdown cells. First exercise. So this is an exercise where you can run the function that is posted in the Julia program, or you can actually use Julia as a scientific calculator, where we only ask here for 3 steps of the bisection method. You could also, and the basic thing here is that you see the steps in the algorithm, that you get familiar with the rule. Most importantly, all the numbers have to be listed with 4 significant decimal places after the rounding. So here we interpret this for this example as 4 places after the dot. All right, we got started. So let's analyze how good is this method. So what can we say about the accuracy? Well, we have an initial bound on the accuracy. So we have the length of the interval. And you can say that half of if you apply rounding, then the middle of the last interval is actually, the middle of the interval is actually the best approximation that you have for the root. So in every step, the interval gets cut in half. So you can say that if you do n steps, then the error on the root will be the length of the first interval divided by 2 to the power n plus 1. So you have the midpoint that you take as your final result. So that is the accuracy. What is the cost? The cost is that we do 1 new function evaluation per step. Sometimes when we look at the cost, we count the number of additions and multiplications. For root finding problems, we calculate the number of function evaluations. Because 1 function evaluation, as we will see more towards the end of the course, could be the running of a Runge-Kutta method of solving an initial value problem when we solve boundary value problems. So the function itself could be a program, and you actually count the number of times you have to run that program to get the new function evaluation. So a cosine function is a very nice function, and it seems that this is just as efficient as adding 2 numbers. But in practical scientific applications, the number of function evaluations is actually often the bottleneck. And the second exercise is actually more a coding application, where if you look at the code, if we would backtrack to our educational function, will see that in the application of the rule, we actually are evaluating again twice. So if we evaluate a condition in the if, we do f of a times the f of m, we actually do two function evaluations. So what I'm actually saying, the cost of the algorithm is one new function evaluation per step. That's not true if you look back to our implementation before. So the difference between 1 and 2 may not matter much, and for small examples it really doesn't, and for asymptotic cost analysis it doesn't matter either. But in real life, if you have to wait 1 hour or 2 hours, that matters. The exercise is worthwhile to actually make the code a little bit more efficient by storing the function evaluations at the endpoint. Similarly, that you store the two endpoints A and B, you also store f at A and f at B, two new variables. All right, the next exercise is actually more important. How many steps do you need to do to get a prescribed accuracy or to get a desired accuracy? So this exercise actually leads into this. And this is the type of exercise that you can entirely do with paper and pencil, or actually what you will do in a text cell in Jupyter Notebook. Except, of course, this is a very simple polynomial. If you are a little bit insecure how to evaluate a polynomial by hand, define it as a function and evaluate the f at the endpoints 2 and 3 to solve the first part of the question. So the first part of the question is the application of the intermediate value theorem. That's what the justify means. We remember calculus. And then the second part of this exercise is that you know that in every step, the bisection method gives you one more bit of accuracy. So that's actually the short way, the computer science way of saying about the convergence speed of the bisection method. 1 bit per step, because in each step you actually halve the size of the interval. So the size of the interval is here 1, so you have 1 over 2 to the power 20. So that is 1, 2 to the power 20 is 1 million. So one can run the bisection method, and indeed that could be good, but the justification is consisting writing down the 1 bit per step justification. And also saying that the initial size of the interval is 1. All right, very good actually, 1 bit per step. That was our first method, not bad. Can we do better? Of course we can do better, otherwise the lecture would be over. So, and we still have about half an hour in this lecture, so let's continue with looking for ideas for more better performing and more general iterative methods. And this will lead us to fixed point iteration. So what is a fixed point? A fixed point of a function is a function if you evaluate at that point, you get the same point back. What good does that do for us? Well, one other problem-solving technique, we already applied divide and conquer. Another very powerful problem-solving technique is that if you have to solve a problem, look at a similar problem. See if there's a problem that is related. And why is that useful, the fixed point view? Well, if we can see that the root finding problem is a fixed point computation, and here you can see the example. So we start with a nice cubic. We see that the x, if we isolate the x, and if we rewrite the equation equals 0, we can actually rewrite this as an equality of two expressions. So if we solve the fx equals 0, we may as well also have solved the gx equals x. So the fixed point equation that we will use g for is actually equivalent to the root finding equation. And what does this buy us? Well, we can evaluate functions also. And actually, fixed point formulas give us actually fixed point iterations. So in some sense, it's much simpler than the bisection method. So we just evaluate a function. And if there is a fixed point, if that iteration converges, at the end you don't see the difference between the function value and the result and where you evaluate it, then actually you have a fixed point. And if the fixed point equation corresponds to the root find equation, then you have found the root. Okay, we actually now have a very simple formula, a very simple method, even simpler. So from a computer science perspective, we have simpler code. And also, actually, the cost per step is only one step. So actually, this looks extremely promising. Let's start to code it up. So here is our next function. For the bisection method, we were kind of wordy, so we wrote in plain English. Here, another way to design functions is to think very carefully about the input parameters and the output parameters, and write this down in a formalized manner. So the spaces, so in the code, Julia is actually not that strict as Python, so therefore you have to put the end everywhere. But actually in the documentation, it often is worthwhile to actually use the 4 spaces, because in the documentation string of the help, it actually then shows up kind of neatly. So using the 4 spaces and the new line strategically can get you to nicely documented code. So you can also think about an example. So that's another way. So if you read the documentation string from the bottom up, you think about an example, and you think about what will you require from the user. You will require the function, and actually functions in Julia are actually very, very efficient. So just as you would write them down in mathematical terms. So the example actually will give you very correct Julia code, if the fixed point at the bottom here is correctly implemented, of course. So the function is the first input parameter. Then the second parameter is the where you start. So that's actually often quite critical. Where you start, so you have a guess now. So we don't have an interval like with the bisection method. We kind of have an idea where we want to find the root. The third parameter is then controlling the fact that we don't want to look into, we don't want to run into a loop that doesn't terminate. And then we have the accuracy. So we actually check how far we are from our fixed point. Here I actually explicitly list the stopping criteria. So I should probably have written this down earlier or sooner. In mathematical notation, one has that we can check the convergence or see whether it diverges always by checking the absolute value of the difference between the function value and the argument of the function. Now we return, of course, the current approximation, but we also want to indicate whether we failed or not. If we fail to meet the accuracy, the desired accuracy, then the fail will be true. Otherwise, the fail will be false. And in that case, actually, the number of iterations that we do is also useful to know. All right, so that's a potential design for this fixed point iteration method. Then actually the definition fits on one slide. So we have one loop in which we actually evaluate the function. So actually the core of the algorithm is actually consisting of these two lines here, where we keep into account that we have the previous value and the next value. So these are the two variables that we maintain because we want to check the error. So we have an estimate for the error here. And then, of course, there is the usual formatting. So the numbers, the integers, are formatted in decimal point. We have the actual approximation, which is now with exponential, with the scientific format. Again, we are here happy when we get 4 decimal places. The errors are written with 2 decimal places, just to emphasize that the fraction part is certainly no more important than the exponent. All right, then we have the main program. So this is also posted and one can copy and paste inside a Jupyter notebook. Do not copy and paste everything into one execution cell. Please do one function per cell. We have 3 examples here. So the first example is the example we started with, and then we have 2 other examples. So let me go through them now. So here we have the first example, and we run it, and actually it's good that we had a bound on the number of iterations, because what you see is the first column is the step. We started at 0.5, but we ended up oscillating between 0 and 1. So you can kind of see the even steps you are at 0 and the odd steps you are at 1. So here we have not a diverging method, but it's an oscillating method. So we will see that makes for a very nice plot. A very, very annoying computation, because we actually know that there is a fixed point as there is a root. There is a real root. I should have probably pointed this out. This is a equation of degree 3, and we know that there is at least one real root. So the other 2 may be complex conjugated, but we were expecting somewhere a root, and we didn't see anything. All right, so here I have a more cumbersome fixed point iteration, and here actually you see that it converges, and is also similar to the fixed point, to the bisection method. So you see actually it converges actually a bit slower, because if you like, we need 4 or 5 or, well, here I see almost 6, 7 iterations to get 1 decimal place. So this is a fixed point iteration that converges linearly, albeit slowly. So now we start to lose a little bit courage in this fixed point iteration, because we had something that oscillated, and here we have something that converges even slower than the bisection method. But wait, let's do a little bit. Let's try something. So the cube root is something that you could have come up with if you picked the x to the power 3 to invert with. There is another way how to rewrite this equation into a fixed point equation. And here the derivation is listed. So it looks very, very far-fetched. But don't worry, we will get to, we will see in later lectures. I will not, will keep you in suspense a little bit. I will not say how to construct this in a more systematic manner. But here you see actually that we have something that is really great. So you can see that in every step, so the last column again is the error. You see that in every step we actually achieve a doubling of the accuracy. So the error actually gets the order of the error, so the exponent, so not the error itself. So with the bisection method, we cut the interval in half and we gain 1 bit in every step. Here actually we cut the exponent. So we actually the number actually gets smaller. So in some sense you can see that you almost get the root to the full precision after 5 steps. So we will call this a quadratically converging method. All right, so all starting with a very, very simple idea of evaluating a function. And we got 3 different methods. Can we think about this a little bit? Now, why was this happening? Were we just lucky? Well, let's start making pictures. So here is another motivation for the Jupyter notebook. One can make very nice pictures interactively. And what is it actually what we are doing when we are running a fixed point? Well, here you see the function g, our fixed point, drawn in blue. And in red, we have the what is called the equation y equals x. So the fixed point is where the red line meets the blue curve. So the red line is also called a bisector because it's bisecting the first quadrant. The plots are all a little bit strange because the as you can see, the red line, it should actually go up in an angle of 45 degrees, but the angle is kind of slanted. That's because of the slides. But you see, when we execute one step, when we evaluate, so when we go from x0 to x1, we can interpret this of evaluating the function is going upwards. So you are at the 0.5 here, if you look at the picture. We evaluate, so we ignore the red line, we go up, or actually we go down if the blue curve would be negative. But we go towards the blue curve in a vertical movement. And then we intersect. So we actually, we are going to the bisector, the red line, in a horizontal fashion. So this is one move, one geometric visualization of one step in our fixed point iteration. And you see the title, this turns into a cobweb diagram. So our first iteration actually was very, very strange. We had an oscillating iterative method, so neither diverging, neither converging. And you can see the cobweb, the name the cobweb getting in here. So we oscillate between 0 and 1. So, and by the way, here I start at 0.5. The code is posted, so it might be tempting to actually start closer. So you could also argue, well, wait, 0.5 is actually rather far from that fixed point, and this is not a good way to do it. do things, but we will see that even if you get very close, you will still not have convergence. All right, so let's look at the cobweb diagram for the next method. So the examples are actually well chosen because the pictures look nice. So here you have a nice cobweb diagram. So we are converging in a spiral way, spiral-wise fashion to the fixed point. So the scale of the plots is kind of strange because of the format of the slides, but you can, if you compare this picture to the blue curve with what we saw on the previous slide, then you can see that the blue curve is actually flatter. And that's kind of a geometric hint at what is to come. So let's look at the last one. So the last really strange thing that we derived, where there we have a very boring cobweb diagram. I mean, and you may not even see the cobweb coming there because we are converging so fast to our fixed point. And here, what is the difference between the three plots? Well, here actually you can see that at the fixed point, the blue line, the blue curve is actually quite flat. And we will make that more precise in a minute. All right, so the Jupyter notebook is posted. Seeing is believing, so geometric interpretations are very important, so we can get some intuition and some interpretation. So the plotting is very important, but also the documentation, so how the numbers are justified. On Monday, exercise 0 was install Julia and Jupyter on your computer. So we will be using the plots and the PyPlot. If you are working on a fresh Julia installation, then you will have to install this. And this has to be done only once and for all. So if you run Julia in the cloud on CodeCalc, this does not concern the addition of the plots. So just to say, if you would download the posted notebooks in your fresh Julia installation, you may run into the problem that you have to run these two statements first. It's tempting to go straight in and do the homework, but the programs and the notebooks do actually are kind of the important and most important connection between the slides and the exercises. So if one is in a hurry, one can only focus on the slides, and there are indeed many paper and pencil exercises for which reasoning is the most important tool you need, but the code is actually important. All right, so now we get on almost the most important slide. So we will prove a theorem, and although this might sound a bit scary, we can prove the theorem just by our knowledge from calculus. So what do we want? So don't look at the bottom yet. So we want a criterion for convergence. So assume that it converges. So that's the nice thing. So let's assume that it converges. And the point that we want, we label it x subscript infinity. The point could be a transcendental number like pi, and we will never know what the exact value of pi is. So the subscript infinity is kind of appropriate. So then if it converges, and we are in this setup, so the fixed point iteration converges, then how fast does it converge? Well, we compute the error. So we compute the error, the actual error here, because here we have a notation x subscript infinity, the error of the next step, so the k+1 point with the kth point. So at the left of this equation here, we see the actual error. And then we exploit the fact that at x subscript infinity, we have a fixed point. So we can just replace x subscript infinity by g at x subscript infinity. And the xk+1 was simply obtained by evaluating the function. So we have an entity here. And then we can do some trick. So we can divide and multiply with the same number. Doesn't do anything, but it gives us some insight if we remember the definition of the derivative. And again, why do you want a derivative? Remember when we looked at the plots, we actually saw that at the fixed point of the very fast converging method, the function was very flat. And flatness is expressed numerically by derivatives, by the value of the derivative. So you actually, geometrically, you remember from calculus that why do we compute derivatives? Well, we are interested in slopes of tangent lines. So in the limit, we will actually, if we get close enough to the fixed point, we will actually see that this ratio, the ratio between the error in the current step and the error in the next step, is actually the derivative at the fixed point. And that is actually the important relation that we have derived. So I could actually have said that this is the theorem. So in technical notation, this is the theorem. So this is the relationship between the errors, the absolute errors. And the critical factor here is the derivative at the fixed point. So in the oscillating, the very strange first cobweb diagram, I indicated that why didn't we start closer? But here you see that the convergence or divergence or oscillating behavior is entirely determined by the derivative at the fixed point. So here actually that fixed point equation is extremely important. And the theorem is actually phrased to indicate that if you have convergence, then that derivative must be less than 1 strictly. Or you could read the theorem from right to left. If the derivative, if the slope is larger than 1, then your fixed point iteration will diverge. So this is the bottom line of the slide. All right, so this is the most important result that we have derived. So this gives us an interpretation for convergence for iterative methods. Here another exercise for which you have 2 fixed points. And if you have 2 fixed points, so now we have a sine function instead of a cosine, one may wonder to where will we converge, either to 0 here or to 1.895. Now, this exercise has 2 points here. First, if you remember the previous slide, just take the derivative of your fixed point iteration and you can answer it. Or you can actually start running the fixed point iteration and look at the cobweb diagram. So make a plot of the fixed point iteration and you will actually see what happens. All right, my time is about up, and I'm also at the end of my slides.